Okay, guys, so we are going to just sort of talk briefly about the salt bridge that we introduced in our diagram yesterday. So you'll see in the previous video, we had um, drawn this electrochemical cell, and we talked about how we determine which chemicals will get reduced and which will get oxidized. And we also talked about electron flow and about anodes and cathodes and voltmeters and oxidation and reduction, all that good stuff. But the one thing we didn't really talk much about at all really was the salt bridge, other than that it contains an inert chemical, in this case, sodium nitrate. So what I wanted to do was briefly talk about why the salt bridge is needed here. So let's redraw that. Actually, let's just keep that drawing. And what I'll do is I'll erase the stuff around it if I can find my pen. There we go. Okay, so let's get rid of this stuff here and over here. And I don't need anodes and cathodes anymore, and get rid of that. And that's pretty good. Okay, so in the salt bridge, we have sodium nitrate. It's usually a paste, actually. So the sodium and nitrate are really just existing as ions. So let's turn this around here. Computer will write a little better. Okay, there we go. That's much better for me. Okay, so we have sodium ions. And nitrate ions floating in there. And so what happens? Well, as the reaction causes copper to reduce, you are losing copper ions from that solution. Now that solution, we talked about this before, you can't just have copper ions floating in there. So that solution might have been by a chemist adding something like copper nitrate, right? So you'd have copper nitrate in solution. And what would be true about that beaker is before you do this experiment, you would have Cu2 plus and two NO3 minuses in there. And so that beaker right now would have a neutral charge, that there would be just as many positive ions as there is, just as much positive charge as there is negative charge, because every copper nitrate would produce one Cu2 plus and two NO3 minuses. So the net charge in there would be zero. But as the reaction is continuing, what would happen is the reaction would be going from copper ions to copper metal, so it's being reduced, and so the amount of copper ions would go down. Now, the reason that's a problem is, remember this, before it was running, this was an equilibrium reaction here. And so think about Le Chatelier's principles. If you decrease the concentration of the copper ions, you're going to reduce the potential of it wanting to be reduced. The other problem you run into is that beaker starts to become more negatively charged, because you're going to have fewer copper ions. So the copper ions would be going down because they are being reduced, but the nitrate ions, they would stay at the same level. So they wouldn't go up or down, they would stay what they are. But if you're losing copper ions, then what's happening is the amount of positive charge in that beaker goes down. And if you think about it, if you're trying to remove, if the cathode is trying to remove, or sorry, this electrode here, if it's trying to take the copper ions and it's pulling them towards it, but then that beaker becomes more negative, well, the beaker is going to actually, the chemicals in the beaker are going to attract, or at least reduce, the ability of the copper ions to migrate towards the copper electrode. So what happens is you get this imbalance of charge as soon as reduction oxidation occurs. So the salt bridge's purpose is to try to stabilize that balance. So you're removing copper ions from solution, so the positive charge is going down. And what you would notice is that the sodium ions in the salt bridge would start to migrate into that beaker. Now, the reason they choose sodium, if you look on the table, sodium is way down near the bottom. under the oxidizing agents. So although you can actually reduce sodium, it's well below the copper ions. So the copper ions are still going to get reduced before the sodium would. So the sodium just moves in there just to maintain the sort of the, I guess, the balance of charge within that beaker. And in the other beaker, what's happening is you're producing zinc ions. And so once again, this solution would have probably been made by maybe something like zinc nitrate. So you would have had some zinc nitrate. So you'd have one zinc ion for every one nitrate ion. Sorry, for every two nitrate ions. And in that beaker, the charge would be balanced initially because you'd have one zinc for every two nitrates. But as the reaction starts to undergo oxidation, you start to produce zinc ions. And so the amount of zinc ions will actually start to go up, and the nitrate would just stay the same. So that means you start having more positive charge in that beaker. And so the more positive it becomes, the harder it would be for zinc to push positive ions into that already positive and growing positive solution. So to maintain the charge stability, the nitrate ions migrate into that beaker. Now, remember we said that oxidation was occurring at the anode and that reduction was occurring at the cathode. So that silly little expression, and ox cared. So the oxidation reaction is occurring at the zinc electrode, which makes this the anode. And the copper is where reduction's occurring, so this is the cathode. And really, once again, remember we talked about why they're called that? The reason you call it the cathode is that cations are moving towards the cathode. And so you can see the copper ions are definitely moving towards the cathode to get reduced, but also the sodium ions are moving towards the beaker with the cathode. And in the other beaker, which you have the zinc being the anode, which is the site of oxidation, you have, now it's hard to see it, but if you look now, the nitrate ions are migrating into that beaker. So you're attracting nitrate ions into that beaker. Now you might say, okay, well, I get the idea that zinc is, or sorry, sodium is really low down. That's not going to get reduced before the copper. But you might be thinking about the nitrate and how does the nitrate play out here? Because if you look on your data table, you actually can see that nitrate's quite high up, but it doesn't react. So I'm gonna let you think about that before our next video. I wanted to keep this one really short. I want to watch a show with my wife right now. So I'm going to just leave you with this little question, which is, why does nitrate not react? Why do you think nitrate doesn't react? So give it some thought, and I'll probably have another video tonight because I've got nothing else to do. So I'll just make another exciting video and post that also. So you can just hang in there for a little bit.